Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Isaac Cheng, Tyrone Woods, and Patrick Côté with us today. Hello, Isaac, Tyrone, and Pat.
Hey there.
Hello.
Thanks for having us.
Oh, yeah. Well, thank you so much for getting to talk about your very lovely article. We don't get many trios, but we got one today on May 7th of 2024, people. And we'll start off with Isaac. Isaac, what's your geolocation? Where are you at?
So I'm currently home in Ontario, Canada.
Okay.
So I just finished my well, I know now at this time I finished my last semester of undergrad. I've successfully passed my courses. So I'm just vegetating at home right now.
Recharging.
Yes.
Very cool. Very cool. And is summer in the air there in Ontario?
Yeah, I think the weather's gotten quite nice over the past few days.
Very cool. Very cool. And Tyrone, how about you? Where are you located at?
I'm an assistant professor here in Winnipeg, Manitoba at the University of Manitoba as of almost a year to the date, just about. Yeah, it's we got May showers here. I guess.
Well,
it's a little
flowers
blustery,
will be coming.
but we needed the rain. So.
Very cool. And Patrick, where are you located at?
Yes, I'm in Vancouver, in Victoria, British Columbia, on Vancouver Island. I'm an astronomer working at the National Research Council of Canada, and it's a beautiful spring day here in Victoria.
Oh, lovely. So I'm in Phoenix, and we are definitely approaching our summer here. We will hit the triple digits Fahrenheit here very soon. And so, yeah, we are rolling in the Sonoran Desert. And Patrick, let's start with you. What do you like to do for research?
So my research interests are mainly focused on the local universe. I study galaxies, globular star clusters, nuclear star clusters, and also interested in nearby galaxies, satellites of the Milky Way.
Very cool. Very cool. And Tyrone, what do you like to do?
Yeah, so I like to learn about why things explode violently and how they produce things like black holes and neutron stars and how that shapes their environment around them from the local universe all the way out to cosmic dawn. So I started out mostly in theory and kind of wandered into observations and then wandered from there into working on new instrumentation. And that's
oh my goodness, you're the proverbial triple threat, a theorist, an observer, and instrumentation.
Sequentially.
My gosh, scary. And Isaac, what do you like to do for research?
Yeah, so I'm going into grad school, so I think maybe at this moment in time, it's like what doesn't interest me is a very small list. So I think I am interested in everything, but perhaps maybe I'm most interested currently in like galaxy formation, evolution, that sort of field. So I hope to pursue that in graduate school.
Very cool. Where are you going to grad school?
I'm going to Caltech.
Oh, congratulations. Very good. Awesome.
Thanks.
You'll enjoy that weather change from Ontario to Pasadena.
Yeah.
Very cool. And that is going to bring us to this very awesome AJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. FORECASTOR 1. Finding optics requirements and exposure times for the Cosmological Advanced Survey Telescope for optical and UV research mission. And Isaac, Tyrone, and Patrick, take us away.
Yeah, maybe I'll kick things off with just a little introduction. So the idea here is for a long time now, we've been, the UV has been an incredibly important part of astronomy. Everything from if you want to understand star formation in galaxies, if you want to understand AGN, active galactic nuclei, if you want to understand habitability of exoplanets, right? You have stellar flaring and things like that. Whatever mass scale you're interested in, you need the ultraviolet. And so people have been a little bit worried because there's been this sort of threat after Hubble, which has been amazing, but won't live forever. After Hubble is gone, what are we going to do in the ultraviolet? We have UVEX that's going to be coming online soon, which will be a great all sky kind of lower resolution kind of mission. But what are we going to do for higher resolution ultraviolet photometry, and also spectroscopic observations coupled to that. And so that's this idea of CASTOR, or the Cosmological Advanced Survey Telescope for Optical and UV Research. And that mouthful is basically a mission that we've been sort of incubating here in Canada for the last dozen years or so. It's finally just finished its phase 0, and we're ready to proceed. The UK Space Agency has also signed a very nice bilateral agreement with the Canadian Space Agency to start pursuing the next steps on getting this ready for launch in 2030-ish or thereabouts.
Nice.
And so to get ready for all of that, and as part of this aforementioned phase 0 study, we wanted to start building the tools which our community is going to need in order to predict, okay, what is CASTOR going to be able to do? How do we engineer this to make sure it can satisfy all of our science requirements? Again, everything from exoplanets to distant black holes to everything in between.
Yep.
So the idea was, if we're going to do this, we're going to do this right. Let's build something that's open source. Let's build something that the whole community can work on. Let's build something that's adaptable, both as we continue to iterate on the mission design and also for any other mission. This isn't going to be the last mission that we ever put up into space.
Very cool.
And so the idea was, let's bind all of these tools together in one place. Something that you can download on your desktop, or you can run off of the Canadian Astronomy Data Center's great CANFAR platform. We'll plug that again and again throughout the paper. And so that's where this idea of FORECASTOR all came together.
Cool.
And so essentially, which is just finding optics requirements and exposure times for CASTOR. And so that's where Isaac enters the story. So he came as a co-op student in, correct me if I'm wrong, Isaac, it was January 2022?
Yes, I think so.
I think that's right. Yeah. And so from there, our initial idea was just, Isaac, let's get you doing some very basic, exposure time calculations, and we'll generalize from there. But wow, did Isaac really run away with this, and just done an amazing job. Of course, this isn't just Isaac and Pat Côté and I. So this is a huge team, including very happy to say a lot of students and postdocs, not just Isaac and at the time myself, I'm now a faculty, but at the time I started, I was a postdoc in the Basket Fellowship Program at NRC, but also students like Jennifer Glover, Dan and Jay Bansal, Laurie Amon, and all at the National Research Council of Canada, as well as students like Cameron Lawler Forsyth and Nolan Dixon and Cameron Morgan, at a degeneracy of Camerons. And other students, as well as postdocs like Madeline Marshall, Melissa Amanouche, Viraja Katu, both at NRC and right across the country. So really, if we're going to build a new telescope for the next generation, let's foster the next generation of science.
Absolutely.
And I think that's also, sorry?
Because with a 2030 launch phase, you need some time.
Exactly. It's not so many years away now, but it creeps up on you. But
Isaac will have his PhD by then.
Yeah, that's right.
Yeah,
Perfect.
hopefully.
And yeah, so that's basically the core idea around FORECASTOR. Maybe if we wanted to scroll down a little bit, we can talk a little bit more about what CASTOR itself is going to look like. So the preamble here talks a little bit about the history of UV astronomy. But if you go down to Figure 1.
Yeah, let's go down and take a look at the filters.
So essentially this is CASTOR will have spectroscopic capabilities as well. Maybe let Pat talk a bit about that in section 2. But for the FORECASTOR ETC in its first iteration, we're really just focusing on the photometry for now. So what we're talking about is essentially we're going to have simultaneous viewing in 3 bands, UV, U, and G, and this is roughly the wavelength range that we're covering. We're also going to have an optional filter that you can roll into place, which will split the UV and the U bands, so you can get UV slopes and things like that, depending on what your science case is.
Right.
So this is roughly the wavelength range that we're talking about, from far UV-ish all the way up to the middle of the G band, which is incredibly valuable when we're talking about matching CASTOR images to all of the other big wide field astronomy missions that are going to be out there. CASTOR is going to be a 1-meter telescope that's going to have a quarter of a square degree roughly field of view, so very compatible with other presently ongoing infrared missions like Euclid and Roman, and also very handy with that G band for matching with LSST data.
Indeed. Very cool. Very good.
Yeah.
Okay.
So maybe if we scroll down a little bit.
Yeah, there's our filter response.
Yeah.
CASTOR.
So here's the CASTOR reference design. What might be best for this section actually is if you just went down to table 1, I think, summarizes essentially the baseball card stats for CASTOR, which are kind of all of the default parameters. And Pat, maybe if you wanted to give a quick overview of just anything that I hadn't covered yet in terms of what CASTOR is going to look like, also the spectroscopic capabilities.
Yes.
Sure. Yeah, so as Tyrone mentioned, CASTOR is a 1 meter telescope, 1 meter diameter. The plan for this is we've designed the telescope so that it uses a 3-mirror and a stigmat design. So what that does is it tries to compensate, give the best possible image quality over a large field of view. In the case of CASTOR, it's about 1/4 of a square degree.
Cool.
And it's trying to compensate for the main aberrations in the telescope, so spherical aberration, astigmatism, and coma.
Yep.
Uses a 3-mirror system, a primary, a secondary, a tertiary. It also uses a fine steering mirror to stabilize the spacecraft, because what we're interested in is trying to have the best possible image quality over this very large field of view.
Okay.
So compared to a mission like UVEX, UVEX has a very large field of view, will operate in the UV, but the price you pay for that is you have less sharp images.
Yes.
We're trying to fill a niche where we want Hubble quality image quality, but over a much larger field of view, about 100 times larger. And this is to match, say, Roman and Euclid in that longer wavelengths.
Right.
So CASTOR is designed for a 5-year mission, lifetime, hopefully longer. It would be launched into a low Earth, sun-synchronous, dawn-dusk orbit. So always pointing away from the sun and highly inclined polar orbit. So you're always pointing away from the sun, and the idea there is you have good efficiency for surveys. We use beam splitters to divide the incoming light into 3 focal planes. And this will be the focus of this paper that Isaac's going to discuss in a minute. This is FORECASTOR 1 in this paper series. There will be other FORECASTOR papers on other observing modes, but for this purpose, we're really talking about imaging, the imaging modes. So we use these beam splitters and we divide the light, as you saw in that figure a moment ago, into 3 broad channels: a UV, a U band, something like the U band, not precisely, and then a G band. So from 150 to 550 nanometers. And that allows us to optimize the system over that fairly restricted wavelength range to get the maximum throughput, which is important. And in this particular table here, you're seeing some of the specifications for the current configuration of the telescope, including the sharpness of the images, which you see is a full width half maximum of 0.15 arc seconds. So not quite as good as Hubble, but close. Pixel scale of 0.1 arc seconds. And the detector parameters like dark current and read noise are baselined to the next generation of CMOS, large format CMOS detectors.
Okay. Yep.
And I think that covers most of what I wanted to say in section 2. And I think at this point, Isaac, I'll turn it over to you.
Cool.
Yeah, so thanks. So I think maybe if you scroll up to the previous page, I can kind of introduce my part or my role in this collaboration, and it was to create an open source exposure time calculator so we can better understand, the performance of CASTOR, and as well as, how we might need to tune or change different parameters to meet the science goals.
Cool.
So I'll briefly talk about each of the parts of the ETC, and then I'll talk about I'll give a brief overview of how we can use the ETC to different example science cases. And I just want to mention that when we were discussing how to build this ETC, we really wanted to emphasize and put a big focus on user adaptability and being able to extend this ETC to perhaps even other missions.
Yeah.
So you'll see a lot of this this philosophy in our different ETC object classes.
Okay.
Yeah,
Cool.
I just wanted to avoid using word object classes before I introduce it, but I will introduce it now.
I'm okay with the term. It's okay.
So in our ETC, we split up the calculations into these different objects. So we have like a telescope object, a background object, a source, and then for this paper, a photometry object as well.
Right.
So splitting the ETC up into these 4 categories allows, a much more modular approach to
Yep.
how we do our calculations. So I guess I'll start with the telescope object first.
Okay.
So the first step in running an ETC calculation is always to make a telescope object that represents the physical telescope that's used for the mission.
Mhm.
So if you scroll to, I think, figure 2,
Let's take a look.
uh,
Table 1 and figure 2. There we go. PSFs. And
right. So this shows the nominal central PSF for each of CASTOR's filters,
Okay.
but it also, as Dr. Côté mentioned in table 1, you have these long list of parameters. These are just the default telescope parameters, which we've set for convenience, but the user can overwrite and update any of these telescope parameters to their heart's content. And I think that makes this really adaptable for other science missions, which we'll discuss in Appendix B. I'm trying to think of where to plug it.
Yeah. No, good.
And then so the sorry, my brain is
We're
going
good.
overdrive right
Isaac.
now.
Take your time. Take your time. It's all good.
So the user, once they've specified, for example, their filter throughputs, the
Okay.
telescope object will automatically calculate stuff like the 0 point and the pivot wavelength
Okay.
and all of the associated physically relevant parameters for our calculations, so that it's very easy to change telescope parameters on the fly and use it for different calculations. And then I think maybe this section would be best summarized in figure 3, I think, I think it's the following page.
Figure 3. Looks like I've got some Stokes and GUIs. Figure 3. Oh, here we go. This is a money shot. Okay.
Yeah, so this is just like a brief overview of the software execution flow for this exposure time calculator. So we always begin with a telescope class. So like I mentioned, the 0 points, pivot wavelengths, they're automatically calculated from passband response curves. You can update and change your point spread functions if you want. You can, again, everything is customizable. And then you also, the next step would be to define something to represent the sky background.
Okay.
So that's composed of 3 different elements. You have zodiacal light, earth shine, and geocoronal emission or air glow.
Mhm.
So you can specify parameters for all of these. You can upload your own spectra for example, the earth shine, geocoronal, and zodiacal light.
Yeah.
So by default, we use HST spectra to set as this background values, but again, like it's not fixed to that.
Uh-huh. Good.
And then you also have your source class. So that is to represent the physical source that you're going to be imaging. So you have various different source classes, like the point source class, extended source. So point sources are like stars, extended sources could be like a diffuse nebula, and then galaxies, which is like an extended source, but with a Sirsic profile.
Okay.
Yeah.
Mhm.
So I'll mention that these 3 source classes that we've mentioned here the point source, extended source, and galaxy source classes. Those you can generate start to finish all in the ETC. But let's say you have something slightly more complicated, like a crowded field, then the user can upload their own, image of a crowded field, for example,
Okay.
using something called a custom source class. And then for example, the telescope, the image resolution will be linearly interpolated to the telescope resolution so that you can still use the rest of the functionality of the ETC, like aperture selection, background estimation, noise values, all of that with your own images.
And it's like a hook. Very good. Cool. Good. Nice.
Right. So after you've created your sources by, specifying, your spectra, modifying it, like you might want to renormalize your spectrum. You might want to add emission lines of various different line profiles as well.
Okay.
You might want to redshift the wavelengths.
Good.
After you've done all of that, then the last step in the ETC is to incorporate these three classes, the telescope, the background, and source, into photometry.
Okay.
And this is what
Yep.
the rest of the science cases that I'll mention later on, this is what it focuses on. So the photometry class, you have a choice of different apertures. So
Cool.
these apertures use fractional pixel contributions as well to have a better accuracy. So by fractional pixel contribution, I mean, let's say you have a circular aperture, the weight of that pixel will be the fraction of the aperture that is actually part of the pixel, or the fraction of the pixel that is part of the aperture. That's what I meant.
I'm with you. Good. Cool.
Right. So I use the term optimal aperture here. So that is just an aperture that maximizes the signal to noise for a point source, with some assumptions that I talk about in the paper, but I don't think it's necessary to go into that here. You can use an elliptical aperture, you can use rectangular apertures, and after you've defined an aperture, then what the ETC does is it actually calculates the brightness and the number of electrons that the detector, the number of photoelectrons that are excited on the detector, pixel by pixel. So this is a completely pixel-based exposure time calculator. So if you change, if you set the sky background, you can set it to be spatially varying over the aperture.
Yes.
You can do it pixel by pixel. So if you change anything, even 1 pixel in each of the telescope, source, or background classes, then the photometry calculation will be changed accordingly as well, because the source class is also pixel by pixel defined as well.
Way through. Nice.
So after that, then it uses this pixel by pixel information to calculate, for example, the signal to noise ratio that you get with a given integration time, or the integration time you need to achieve a given signal to noise ratio.
Cool. Very nice. Very nice. Very flexible too, right? I mean, you got a lot of, I think that's one of the selling point here, right? It's very flexible.
Yes. Yeah. And, theoretically, you can adapt this to any, CCD or CMOS based mission.
Very nice.
So this workflow that I've just described, it requires, some programming knowledge. You don't have to, really go into the weeds of each calculation, but it does require you to know Python. So, in case you're not comfortable using Python, or let's say you don't have access to your laptop to run a Python instance, and you want to be able to quickly check an ETC calculation on your phone or a tablet, then we've also developed a graphical user interface shown in figure 4, if you scroll down.
Good.
So this shows, just half of the graphical user interface so that you can see the stuff better. But this shows, for example, the Mach source that we've rendered in the top left corner, the elliptical aperture that's rotated on the top right, and then like the passband, as well as the source spectral energy distribution in the bottom over there. So this graphical user interface is hosted on the Canadian Astronomical CADC Data Center, Canadian Astronomy Data Center, CADC, the CanFAR Science Platform. So you can access this, even on your phone, like I was mentioning, and you don't see it here, but there's a other half of the graphical user interface that lets you modify each of the parameters I just discussed above. And as you input and save these different parameters, the right half of the screen, so these plots here, they will update in real time so that you get kind of a more seamless experience when you're doing these pixel-based exposure time estimations.
Cool.
Right. So I think I covered the main parts of the functionality of the ETC. Is there anything that I might have forgotten or you think would have been good to mention?
It's open source, and so is it hosted on GitHub somewhere or what?
Oh, right. So yeah, our code is, I think there's a link somewhere
Probably.
for our GitHub repository. So yes.
Okay.
Yeah. Oh, that CanFAR is where you can access all of the online tools and stuff like that. And then footnote 2 footnote 11 on page 2 is where you have the
2, there it is. Okay, where's our GitHub? There's our GitHub. Okay. So
there you go.
That's the actual source.
Yeah.
If you want to run it, never know when you might want to run this on your iPhone. So yeah. Exactly. Very cool. Very cool. So now you want to maybe do some example science results, maybe?
Yeah, so I'll just quickly interject here, I guess, and point out. So CASTOR is, a 100-person collaboration at this point. There's people from across Canada and around the world who've been working in particular with the recently completed phase 0 study, sorting out exactly how we're going to keep busy in the first 5, hopefully just first and not only 5 years of the mission after launch. So, about 60% of that time is going to be of that 5 years is going to be devoted to legacy surveys. So things like, mapping out the Magellanic Clouds in UV, a couple of different deep fields looking for, huge populations of galaxies, hunting for massive white dwarfs. And so these are just, a smattering of things. Reverberation mapping of AGN is going to be a big one. Many, many different projects that are going to be undertaken immediately upon launch. And so what we thought we'd do, just to sort of show what FORECASTOR can do, is run through just a smattering of some of the science cases, things that could be kind of condensed to just a few paragraphs and sort of punchy format, and just quickly show just what's possible with the FORECASTOR ETC. So if you scroll down a little bit, we can maybe Isaac and Pat and I can loop through some of these, and we can just sort of jump in at random here.
Hors d'oeuvres, CASTOR hors d'oeuvres.
That's right, exactly. To whet the appetite for what CASTOR is going to be.
Let's start off with massive white dwarf.
Exactly. So one of the really cool things that I'm happy we were able to include in this paper was hunting for massive white dwarfs. So as someone who's done a lot of work in population synthesis and trying to understand stellar populations and trying to understand stellar evolution as well, it's the really annoying problem that's been really persistent is we don't know exactly what the turnoff mass is. What's that tipping point between a very, very massive white dwarf and a neutron star, right? Exactly how massive can a star start out and leave behind a white dwarf and not something that's going to collapse, an electron capture supernova or something like that. So what the idea, sort of the gold standard test, and something that was really pushed by Harvey Richer at UBC was, let's go hunting for these very, very massive white dwarfs and clusters, open clusters that look like they're about 40, 60, maybe 80 mega years old, right around where we think that white dwarfs should just start being formed, these most massive ones.
Yes.
And so it turns out, it's very, very hard to be looking for these, still not that bright objects in the Magellanic Clouds with existing facilities.
Okay.
Hubble could do it, but very narrow field of view. Magellanic Clouds, not very far, very far away. So you really want to be, you want something, a wide field instrument in order to be looking for these. And so it turns out CASTOR is going to be an incredibly powerful machine for hunting down massive white dwarfs, some of the most massive white dwarfs in these particular age clusters. If you scroll down a little bit to the next figure, I think it's figure 5.
Yeah, figure 5.
Yeah, so here we side by side. So this is table 2, which is sort of just showing us, how long it will take to reach signal to noise of 5 in a given magnitude in a given CASTOR band generically for different bands, and you can see for different magnitudes, and you can see CASTOR can get very, very deep very, very quickly, and so we're talking about a limiting magnitude of around, what is it, around in 4,200 seconds, for instance, a little over 28, which is going to be plenty for, say, in the Magellanic Clouds, looking for very, very early, very, very young, very, very massive white dwarfs. I'm very happy that we could include this section, not just because it's a great illustration of what CASTOR can do, but because, of course, we unfortunately lost Harvey Richer during the final publication of this paper, and he is just an incredibly important driver of not just Canadian astronomy and Canadian space observations in particular. I think possibly our heaviest user of Hubble data. I think he still holds the record. But also, just a very important force in fostering the next generation of Canadians. And so it was very good to be able to include that.
Thank you, Harvey.
Thank you, Harvey. So if we move on to the next section.
Okay, so massive white dwarfs, flares. That's an interesting one.
Flares, exactly. So that was another thing that CASTOR is going to be able to do, a really, really great job of, is basically monitoring the flaring activity of M dwarfs. So this is a very, very important parameter for understanding, if these very, very numerous M dwarfs are actually good candidates for hosting habitable planets. If you're going to live in the habitable zone of an M dwarf, you've got to be pretty close in. And if these things are flaring in the ultraviolet all the time, it's going to get toasty really fast. And you're probably not going to hang on to your atmosphere there if you had one to begin with. So, understanding this flaring activity, vitally, vitally important. We can maybe keep rolling a little bit here. So this next figure is just sort of, if you scroll down a bit, just showing some of the light curves that we're going to be able to generate. And so we'll be able to, we're going to have very, very good timing resolution with CASTOR. And so we can actually resolve this flaring activity. But I think that's all really maybe.
Yeah, so let me ask you, what is the time resolution you can get on this?
Pat, what is the shortest time resolution that we can get exactly?
Of course,
we can read out well below a second for the main arrays.
Yeah.
Okay. Yeah, and then of course there's cadence on where it points, and that's where all it starts. Very good.
Okay. So rolling right along.
Your field.
I think if we move on down to figure 7. So this is for a section that was contributed from the Stellar Working Group on measuring proper motions for near-field cosmology. So CASTOR is going to have very good spatial resolution, and it's going to be also very, very sensitive. So one of the things that I think is really, really cool, and I know Pat is very excited about this as well, is that it's going to be very good for measuring proper motions of distant stars. And actually, it's going to outperform Gaia for very, very faint objects. For which Gaia really wasn't, designed for. Things that are fainter in the G band than 20.
No slam on Gaia yet, right?
No slam on Gaia, but but this is going to be really, really important for tracing down the faint stars and stellar streams in our Milky Way, and sort of teasing out the assembly history of our Milky Way. I don't know, Pat or Isaac, if you wanted to comment anything else on that.
Yeah, I think really, I think what Dr. Woods just said is really highlighted by the top panel of this figure on the right here. So this shows the astrometric error on the y-axis, and then the CASTOR G band magnitude on the x-axis. So you see, Gaia outperforms CASTOR at brighter objects, but for fainter objects below, G of 20, magnitude of 20, then CASTOR really, really excels in probing these fainter objects.
Big bottom on them too. Very nice.
And the second panel here shows the how accurately we can measure the velocity of these different objects. So, and the vertical lines show that. Sorry, can you scroll down to the description? I think the vertical lines show the
approximate magnitude.
show the G-band magnitude for different distances. Okay. Expected plane of sky velocity precision. Okay, for different distances. And I think the key thing to pay attention here is the 20 kiloparsec line, so the pink lines. So for one of the things we can do with this information is to probe the existence of, subhalos, dark matter subhalos that are starless, so that we can't easily measure from other means, and we can do this by looking at, quote unquote holes that they punch into these stellar streams, and we can determine the streaming motions by looking at the velocities of these stars, and that's what this panel shows here. So CASTOR will be able to uncover like a large population of these stars, and we'll be able to better understand the morphology of the dark matter subhalos that we can infer from these streaming motions.
Yes. Very good. Nice. Thank you.
Great.
So
go ahead, Isaac.
Sorry, go ahead.
No, go ahead, Isaac.
No, I was just thinking about going to the next figure, but if you had anything to add, then.
Anybody? Okay, so we did white dwarfs, we did M flares, we did near field cosmology, and star formation. Definitely.
Awesome.
Right. So
go ahead, Isaac.
In this section, I guess the emphasis is on star formation in galaxies, because most of the UV light in galaxies, as it says here, they're dominated by massive stars, and because CASTOR is uniquely sensitive to the UV over such a wide field of view, it can very efficiently probe the star formation rate and star formation histories of these galaxies.
Cool.
So just as an example, if we look at figure 8 here on the top right, then this shows the exposure time predicted using the FORECASTOR ETC that we've mentioned, that's required to reach a signal to noise ratio of 5. So we mentioned here 2 different surveys, an ultra deep survey and a deep survey. So these are both, proposed surveys for the CASTOR mission.
With you.
And what is the punchline? I'm trying to remember the punchline for this because I didn't write this section.
I would say the punchline is, so this is to demonstrate that there are basically 3 planned galaxy evolution surveys considered for CASTOR. One is a wide survey covering 2,000 square degrees. There's a deep survey covering 80 degrees, and then an ultra deep covering just a extremely deep survey of 1 square degree. And so all of these are trying to use detect star formation within galaxies over a range of redshifts using the UV emission, which is our primary star formation indicator, right? And so this is a mixture. This wedding cake design of surveys is trying to understand the faintest systems in a greater level of detail, and of course build up the statistics at the same time for the nearby universe. And this is what this is showing.
Cool.
Right. And figure 8 ties into figure 9 just below. So we can convert these UV magnitudes into star formation rates using an equation in the paper.
Yes.
And we can see here that
Okay.
both the deep and ultra deep surveys, they can probe the star formation rate for galaxies up to, redshift 2 and beyond, roughly. So out to cosmic noon, which is, the most important time for galaxy formation and evolution because of just the abundance of star formation happening at this point.
Cosmic news.
And because we can have such good spatial resolution with CASTOR as well, and because the ETC is a pixel-based exposure time calculator, we can also predict the spatial distribution, so the spatial signal-to-noise ratio
Yes.
of such galaxies. And using spatially resolved SED fitting techniques, then we can learn a lot more information about galaxies and their star formation histories, star formation rates from that. So if you go to figure 10
Okay.
on the next page, I think.
Yeah. That's how we do the conversion, people. Equation 4, figure 10. Okay.
So this shows, the time required to reach, again, a signal to noise ratio of 5 for each pixel, assuming just, a flat, uniformly lit source. So this shows that we'd be able to probe very deep. Oh, yes, and the top y-axis there is just a conversion using, again, another equation that is just below this figure to convert from your surface brightness into your star formation rates.
Now the star formation rate was 1 up, but okay, very good. Okay, cool. Wow. I'm very optimistic.
Yeah. So this just tells us, for example, that we'd be able to constrain the spectral energy distribution in the UV band to like 27 to a surface brightness of 27 magnitudes per square arc second. So that's like, out to the very faint outskirts of the galaxies. And we can actually see what some of these galaxies look like in the following page. There's many figures there.
Okay. Oh, here we go. This was the one we were looking for. Ooh, here we go. Predicted CASTOR images. There we go. Okay.
Yeah. So these are just some examples of galaxies selected from the Hubble Ultra Deep Field and then simulated using the FORECASTOR predicted noise values and everything that I mentioned before. So these are like mock observations of what different exposure times and passband combinations would look like. So on the left, for example, you see 100-hour observation of in the CASTOR G band in the top right panel, that sort of stuff. Yes. And then on the left, you see these ultra deep field galaxies for a range of redshift and magnitudes at 100-hour simulated observations.
All 100 on this one. Okay, got it. Very nice.
And then maybe Dr. Woods and Dr. Côté can talk about the synergy of CASTOR with, Roman and the other space telescopes using the figure right below figure 11. I think it's, yes. So that RGB color composite right there.
Yeah, so this is, oh, go ahead.
Tyrone.
Go ahead.
No.
Okay. So yeah, this is basically just showing a little 1.5 by 1.5 augmented region of the Hubble Ultra Deep Field, basically mostly for illustrative purposes. This is going to be about the depth that CASTOR is going to be able to reach, but it's 0.06% of the area of the Hubble Ultra Deep Field. right? So imagine stretching that out in the UV. That's going to be game changing, right? And then overlaid on that, we've also showed, one of the Roman filters. CASTOR is going to be just beautifully matched as a UV counterpart to what we're going to be doing with Roman, and already now with Euclid, in terms of providing multi-wavelength coverage of these huge deep fields of galaxies stretching back in time, and really understanding how galaxies evolve over cosmic timescales. Really just sort of a teaser image, basically. I don't know if you wanted to add anything to that,
I
Pat.
want more candy. Yes, very nice.
Yeah.
Very cool. That's a teaser.
Yeah.
Anything else? Exposure times for those galaxies?
Yeah, so maybe there's one more science case. In the interest of time, I'll kind of skim through it here. So another thing that we're really excited about for CASTOR is basically reverberation mapping of AGN. So using the timing of variations in the changing flux we get between the central source and the emission lines that we observe, in order to basically precisely map out the area, the radius basically of these emitting regions, probe the actual emitting, structure of the emitting regions, and thereby constrain the mass of the black hole. Using this, CASTOR is going to be able to, very tightly constrain, provide basically benchmark masses for about 1,000 AGN in the core science program over 10 billion years of cosmic history.
Yeah.
So it's going to be, the new go-to, step in the mass measurements ladder as we measure black hole masses across cosmic times. So figure 11 is just sort of showing very quickly here the exposure. Oh, sorry, it's not 11. Sorry, figure 13, just very quickly showing the exposure times needed to reach different magnitudes in different bands for a typical AGN spectrum. You see, we can get very, very deep very quickly. And if you roll down to figure 14, so this is just showing sort of the predicted number of AGN versus the number that we're going to actually be able to observe the distribution. So comparing that with a simulated sample and showing that we're going to be able to actually do this kind of science. So very, very exciting.
Particularly at the low redshift and when it actually gets fainter.
Yes.
Yeah, exactly.
Yes, exactly. Yeah, you're picking up this side of the distribution pretty well.
Yeah. So that's just all I'll say. That to round that out is that that's just a smattering of the really, really cool science cases that CASTOR is going to be able to tackle when it launches in about 2030. So with that, we have the conclusions here, but I wanted to give a little bit of time. I was hoping Isaac could maybe run over a little bit of the appendices that basically teach people how to use FORECASTOR and how to use FORECASTOR and how to use FORECASTOR for other telescopes. So if you wanted to say a few words, Isaac.
Sure. So Appendix A is really to complement Section 3 of the paper, where we just discussed the general software execution scheme. So here we actually go step by step and we simulate a point source, extended source, and a galaxy from start to finish. So like I said again, we start off with a telescope. Here we're not changing any of the telescope parameters. We're just using the default CASTOR reference design values. But as like the next table shows, you can easily adapt that and make it to whatever telescope you want. Then we define, we estimate the sky background for your telescope. So in this case, we have just the default Earth shine and zodiacal light values, but then we also add an air glow line for the Lyman alpha using this syntax here. So you specify wavelength, the line width, and the flux. And this just adds this emission line on top of the background spectrum.
Yes. There you go.
And then for the next part.
Okay. Point sources.
Yes. So here, point source is probably the easiest to simulate, in the sense that, all you have to say is, I want to create a point source, and you might want to renormalize it to a specific AB magnitude, you might want to shift the spectrum
Okay.
a little bit. And in this case, we're assuming a point source is a black body.
Okay.
So I think that's in the next part of the
Yes.
example.
Mm-hmm.
And then we're adding emission lines to the black body
Yes.
in the following table. Yes. So we add like one with a Gaussian line profile and another with a Lorentzian line profile. And then you can see, what that looks like in figure above, figure 15. Yeah.
Very good. And yes, it does. Weirdly broad. Mhm.
Yes. Yeah. I mean, they're weirdly broad just so you can more easily see by eye the shape of the emission line profile.
Yeah.
An artificial example. It's okay.
Yeah, I understood. I understood. I think this is the only time in the APJ I've ever read weirdly broad. So you win some sort of a prize for that. Very cool. Okay.
Yeah, I think maybe I can just skim through the rest of them, just in the interest of time. I don't know how long it's been, but
We're doing great.
then we can do the same thing with extended sources. So extended sources, we're assuming it's uniform surface brightness within some, ellipse.
Yes.
But you can, create your own function and make it into an arbitrary surface brightness profile,
Yes.
which I describe in more detail in section 3.
Yes.
And then
That was that. All right.
same thing with galaxies. You specify your effective radius, so your half-light radius, and your Sirsic index. And then I think we can skip to maybe figure 16. That would show what these sources look like.
Oh, there we go. Here we go.
Yeah.
Mm-hmm. Nice.
So here we're using an quote-unquote optimal aperture that maximizes the signal to noise ratio for a point source on the left, and then we're using a rectangular aperture in the center, and then an elliptical aperture on the right.
Okay.
And we've calculated the encircled energy, the AB magnitudes, and the time to reach a given signal to noise ratio in table 3, as well as the signal to noise ratio after some integration time.
Okay. That looks strangely like pi.
Yes, that was also intentional.
I don't think, yeah. Yeah, 4 digits, not intentional. Or intentional. Very cool. Very good.
And then perhaps one of the most significant aspects of FORECASTOR is that it can be easily adapted to other missions. So everything I mentioned about the background, the source, photometry, all of those stay the same, and all you have to do to adapt it to your mission is to define your own telescope instance.
Yes.
So here, this gigantic code block here just lists out a dictionary of parameters that you can
Cool.
tune.
Uh-huh.
And then once you've specified these, you keep the rest of your code the same and just point it to different telescope instance.
Very cool.
So you change one piece of code, and then you can use it for a completely different mission with different parameters.
Nice. Very good. Very good. Beautiful work, Isaac.
Yes, even though I'll just echo that it was a collaborative effort, and Dr. Woods and Dr. Côté provided a huge amount of guidance for this project.
Okay, beautiful work, Tyrone and Patrick. Good job. Very cool. Very, very cool. All right, Isaac, Tyrone, Patrick, I want to thank you so much for walking us through your very awesome FORECASTOR article. Thank you.
Thanks to you. Thanks to AAS Journals too.
Thanks very much for having us.
Sure.
Yes, thanks for this
kinda hinted
opportunity.
at it. You kind of hinted at it a little bit, and it's sort of blatantly obvious from the title. But let me push on it a little bit. So where do you think we go from here, given the published article? It says FORECASTOR 1, so presumably there's a 2. Presumably there will be some spectra. And
Exactly.
so I guess let me ask, where does this project go? And FORECASTOR sort of, let's say, between now and, if you want to speculate, to launch.
Right. So in the next little while, the idea is we already have a paper that's actually about ready to resubmit, which is covering basically detailed image simulations. So now let's actually draw from catalogs, from semi-analytic models. Let's
Oh,
get
yeah.
a real idea of what the galaxy population over cosmic time is going to look like, and let's simulate the performance of specifically the CASTOR wide, deep, and ultra deep surveys. So watch for FORECASTOR 2, pretty much any day now.
Cool.
Beyond that, there'll be other FORECASTOR papers covering the performance of the GRISM instrument that we didn't get too much time to talk about. So we mentioned that there was a filter you could rotate in order to split the UV and U. You
Yes.
can rotate it one more time and have a GRISM spectrograph in place and actually get GRISM spectroscopy over the whole UV and U fields of view. There's also going to be a parallel instrument, which is a DMD or digital micromirror device driven UV MOS, so multi-object spectrograph.
Right.
Basically, that's a whole mouthful of acronyms. That means we're going to be able to take a whole lot of different spectra that we can define on the fly for a number of, many, many different objects. There'll also be papers from the FORECASTOR series coming out describing the scheduling of the surveys in detail, which is a very, very
Very
fun, very complicated traveling salesman problem, basically.
We've had a couple of videos on solving that.
I know.
Traveling telescope problem, the traveling telescope problem. Right?
It's non-trivial. It's a lot of fun. And those are great videos. And beyond that, there'll be and beyond that, there'll be more and more coming out defining the precise plans for the mission in the run up to launch. Yeah, I don't know. That's the plan for FORECASTOR overall, and then of course when CASTOR launches, all bets are off. It's going to be an enormously impactful instrument.
Yeah, very cool. Well, it's going to be so exciting to see CASTOR develop over the next couple of years and run up to launch. It'll be very exciting to have that kind of instrument available again and with even better parameters than previous ones. So congratulations to the team. It's very wonderful. Isaac, Tyrone, Patrick, thank you so much for walking us through your very lovely article.
Thanks very much.
Thanks.
Thanks so much.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.